Transition states are extremely important for chemists to understand how reactions proceed, and that's why their location and also analysis is a very important computational chemistry task. And luckily, MLatom enables to perform such calculations with very different methods. As we've seen before in this overview, MLatom provides a wide range of methods from quantum mechanical methods, semi-empirical methods, DFT and ab initio, to hybrid QM and machine learning approaches like AIQM1, to pre-trained machine learning models, and also from using your own models which you can train yourself. And the tutorial for optimization of transition states and the analysis with MLatom you can find online in the MLatom website and XACS website, and if you click on the menu on the transition states tutorial, you will find here how to perform such simulations, and I will show you an example of Diels-Alder reaction between ethylene and 1,3-butadiene, how to do this. And here we use very popular semi-empirical GFN2-xTB method. And I should know that GFN2-xTB method is implemented in a very nice program XTB, but this program does not provide by itself any way to do transition state geometry optimizations. So MLatom does it for you by interface to XTB program. And to start with, you need some good initial guess that will make it easier to optimize the transition state. And here we provide it for you. And then the input file is very simple. It is just requesting this GFN2-xTB method, request transition state geometry optimization. Then you need to provide this initial guess, which you can download. And then when you have this input file and you have this initial guess of transition state, you can upload it first to auxiliary files, and you can put your input file here, and then you submit the job after you give it a name like TS search. And we need some special characters here. Okay, so we submitted this job, and while it is optimizing this geometry, I can already show you what you can get with it. So output will be from your local computer. If you use, for example, Gaussian optimizer like this, after 7 optimization cycles, you will get the final geometry, which would look like this, and you can compare by downloading it from our website. Note that we do not implement ourselves optimization of transition states, so we rely on Gaussian program or ASE program, and if you use Gaussian program, then you will get output as you saw before. If you use ASE optimizer, it uses dimer method, and with this dimer method it will take you more cycles, and also because of random seed you will get a bit different structure. So going back to the tutorial, you can also use MLatom in your Python script, and then you just need to put in, when you do geometry optimizations, additional argument TS equal true, and then it will does the same as with input file, so you should get the same structure at the end. And of course, after you optimized it, you need to check your geometry, and to do it, you basically have to run frequency calculations. We have a separate tutorial on this, which you can check how to do it, but that's very simple. After you optimize geometry, you just put it here, and then you request frequency calculations. Once you've done this, you will get your output file. Again, we will use Gaussian here, and then you can analyze your Gaussian output file as usual, so you can visualize the vibration, see whether it looks reasonable. In this case, obviously, transition states looks very reasonable. It does what it should do, so it forms these bonds, and then it goes away. But more rigorous way to check it also to perform IRC calculations, which we also do through the Gaussian interface. And that would be very simple with MLatom input. So you do IRC keyword, put your method with which you want to do this, and then you provide the optimized transition state. You can also do it in Python the same way, and then you will get some IRC curve. Now there are some complicated cases because transition states not always easy to find, and if you want to do something more advanced, like using QST3 option in Gaussian, then you can also check in this tutorial how to do it. Basically, you would need to modify this Gaussian.com file, put what you want to do, and just don't touch these lines which you will get from previous calculations with MLatom. After this, you can check your result, and as usual. And basically, I've shown you example with XTB, but you can also use Gaussian for different quantum mechanical methods, or here PySCF to do bis relief geometry optimizations, for example. Or you can also use AIQM1, which would provide you similar speed to XTB, but from our previous benchmark, which you can read more in detail, we know that AIQM1 gives you quite good results for transition state geometries. You can check it later in the paper if you're interested. But basically, there are many different options. You can use MLatom. Also, you can try to optimize geometry with machine learning models if you train them on some data sets, but that's more advanced. So if you have any questions or comments, please ask us in the usual channels, which you will find in the description to the video, and ask us also in via email and Slack channels.